Hello, this is Mr. Sherman, and I'm here today to talk a little bit about the methods we've been learning about finding sequences, particularly when they are based on polynomials. So to get started, what I want to do is take a look at the basic sequences that our polynomials are built upon, where we look at the sequence where we just choose a number n, and n gets bigger, 1, 2, 3, 4, 5, 6, or we look at n squared, and n squared goes 1, 4, 9, 16, and so forth. And then we look at the n cubed terms, if we take a number and multiply it 3 times, or we take a number and multiply it 4 times. And what I'm interested in doing with each of these is taking consecutive differences until we have a constant, and then looking at each result and seeing if we have a pattern that generalizes, that we could even perhaps predict what the pattern is going to be for n to the fifth or n to the sixth, and so forth. So we will start here with n, where we just have 1, 2, 3, 4, 5, 6, a very simple sequence, and we're going to take consecutive differences, something I can imagine you can do in your head. And we discover that in one step we have a constant, and that constant value is 1. I'm going to call that our baseline value, because if we end up with another sequence built on n, we are going to compare it with the baseline value to try to figure out what the coefficient needs to be. And we'll see that in action in the second half of the video. So let's move ahead to n squared. And again, we're just going to take constant differences. We see a neat little pattern here. When we take the difference between squares, we just get consecutive odd numbers. And then if we take differences again, we get the constant value 2. So when we're dealing with an n squared sequence, we discover it takes 2 steps to get to a constant value, something all of you were already familiar with. And now our baseline value is 2. So if we are doing constant differences and we think it's an n squared sequence and we come down to a constant value of 2, the coefficient is actually 1. Whereas if we had an n squared sequence and we came down to a constant value of 10, we would think the coefficient is going to be 5. And again, we will see that in action later with our real sequence. So now we move to n cubed. Taking constant differences, we get 7, 19, 37, 67, 91. Differences again. Now a pattern is starting to emerge. And one more time, and we have reached our constant value. This time our constant baseline value is 6. And so we realize that if we're dealing with an n cubed sequence, we expect it to take 3 steps to get to a constant value, and we will compare whatever that constant value is with 6. For example, if we took 3 steps to get to a constant value, and that constant value was negative 12, we might expect the coefficient in front of n cubed was going to be negative 2, because negative 12 divided by 6 is negative 2. So let's look at n to the fourth. Numbers are getting fairly large here, but I have worked out the subtractions ahead of time. So the first step, we have some still what look to be fairly big numbers, and I don't really see a pattern emerging yet, other than the fact that I see some 5s in the unit digit originally. 2 steps, and maybe still no clear pattern. 3 steps, and now I'm starting to see something emerge. And after the 4th step, we end up with a constant value. I probably should have taken the next value also, but if you tried this on your own, I didn't need you subtracting 7 to the 4th power from 6 to the 4th power and so forth. If you try it, if you're interested in trying it, you will discover that you get 24 again and again and again. So it takes 4 steps to get to a constant value. Fitting with our pattern, I'm sure that you could have guessed it would take 4 steps. And the baseline value is now 24. So it's worth noting that the baseline values we've seen so far are 1 for when we just have a 1-step to get to n. For n squared, we found that our baseline value is 2. For n cubed, we found that our baseline value was 6. And for n to the 4th, we find that our baseline value is 24. So this is a different kind of sequence of its own, and it's not actually based on a polynomial. The question I might ask is, can you guess what the baseline value would be if we were to work out n to the 5th? Now, it gets a little bit messy, and we need more values, and so I'm not going to work it out here on the screen, but I used x instead of n, but it's all the same. So if we wanted to talk about x to the 5th or n to the 5th and work out the sequence, it does turn out that it takes 5 steps to a constant value, and the baseline value does turn out to be 120. If you found the pattern earlier, 2 pages back here, to go from 1 to 2, we multiply by 2. To go from 2 to 6, we multiply by 3. To go from 6 to 24, we multiply by 4. And so to go from 24 to 120, we multiply by 5. I will note also that 120 is 5 factorial. 5 times 4 times 3 times 2 times 1 is 120. Now, the good news is I'm not about to give you sequences that are based on 5th degree polynomials because the math just gets a little messy. In any case, so here we go. So now I want to find the formula for this sequence. It is based on a polynomial, so we'd like to find a polynomial sequence, and we'd also like to find the value of the 10th term. I actually encourage everyone to pause the video right now and try to work out the problem on your own. I'd recommend starting with something like this, take consecutive differences, and see if you can continue working that out until you have the sequence. If you get stuck, you can resume the video and watch along until the place you were stuck. And if the video gets you unstuck, then you can pause again and keep going. All right, so I assume you have made as much progress as you can, maybe even solved and found the sequence. But let's look at this. So we take consecutive differences, and the first set looks like this. The second step looks like this, and a pattern perhaps starting to emerge. And after 3 steps, it looks like we get a constant value of 18, which would suggest, since it took 3 steps to get to a constant value, the main term, the term with the highest exponent of the polynomial, is going to be n cubed. And for n cubed, we know that our baseline value is 6. So we divide 18 by 6, and we expect the coefficient in front of n cubed to be 3. So we would love 3n cubed to give us the actual sequence. It doesn't. If we look at what 3n cubed gives us, 1 cubed is 1, times 3 is 3, 2 cubed is 8, times 3 is 24, 3 cubed is 27, times 3 is 81. It doesn't give us the sequence we wanted, but we can take that away from the sequence we wanted, and everything left should be less than a 3rd degree polynomial, maybe 2nd degree, maybe 1st degree. And so let's take that subtraction. So we're subtracting the yellow values from the green values. And we get now a sequence of 5 numbers. They all happen to be negative. That shows what we need to create to reach the green numbers. So far we have the yellow numbers. We'd like to reach the green numbers. So it turns out we need to subtract from all the green or yellow numbers to get the green numbers. So we need a sequence that gives us -3, -1, -1, -3, and -7. So if you have not worked out this next sequence, I would just pretend this is a brand new problem. Ignore everything above the horizontal red line and say we are given the sequence -3, -1, -1, -3, -7, and see if you can find a formula that generates that sequence. And it makes sense to start with consecutive differences again. And one step of differences, remember, we're asking what we go up by as we go left to right. So from -3 to -1, we go up by 2. That is -1 minus -3. From -1 to -1, we go up by 0. And from -1 to -3, we actually go down by 2 or up by -2. -3 minus -1 is -2. And the last term, to go from -3 to -7, we go down by 4. And then we take differences again, and we find that now we get a constant difference of -2. So for the red sequence, it took us 2 steps to get to a constant value. That constant value is -2 to be compared with our baseline value of 2. We do a division. -2 divided by our baseline value is -1. So we expect the coefficient of the n squared term that will generate the red sequence to be -1 times n squared. And so there we have the sequence of -1 times n squared, gives us -1, -4, -9, -16, -25. And as before, we are going to subtract the gray values from the red values. So note that you are subtracting negatives every step along the way. So what we end up with is adding the gray values. Well, not really. We're adding the negation of the gray values. So it acts a lot like addition to the red values to see what we still need to reach our goal. So our goal is the green values. We've found 3n cubed and taken them away. We found -n squared, and we're going to take them away. And so that shows that we need -3 minus -1 is -2. -1 minus -4 is like adding 4 to -1, so that's 3. And then 8, 13, and 18, and so forth. Now we've taken away the n cubed terms. We've taken away the n squared terms. So what's left, we should predict, is not more than linear, meaning it will have n in it, or it might be constant, but this is obviously not constant. So this should be going up by a constant value, and you may not need to use the method to find a formula that gives us -2, 3, 8, 13, 18. We actually do see they're going up by a constant value. But to be systematic, let's go ahead and take constant differences. We see that the constant difference is 5 after only one step. Since it only took one step to a constant difference, we expect this to be n to the first, or just n. Our baseline value for n is 1, so we divide 5 by 1, and we find our coefficient in front of n should be 5. So we now look at that 5 times n. It's just counting by 5s. Skip counting might be called. 5, 10, 15, 20, 25. And so one more time, we're going to subtract the now white values from the gray values above. And we've taken away our n cubed values. We've taken away n squared values. We're taking away n values. So the only thing that should be left is a constant. And so -7 is our constant to go with the terms of the polynomial that we already have. And if we put all of those together, we should have the formula that generates our sequence. We had 3n cubed minus n squared plus 5n minus 7. I encourage you to check out at least a few of the values of n. We have 5 terms in the sequence, so you could put in n equals 1, 2, 3, 4, and 5. I'm just going to talk about 1, 2, and 3 on this video. So if we plug in 1 cubed is 1, so we get 3, minus 1 is 2, plus 5 is 7, minus 7 is 0. So n equals 1 gives us 0, the green value up above, which is what we wanted. If we plug in n equals 2 cubed is 8, times 3 is 24, 2 squared is 4, so 24 minus 4 is 20, 2 times 5 is 10, so that gives us 30. Minus 7 is 23, so 2 gives us the correct value of 23. And finally, n equals 3 is 81, minus 9 is 72, plus 15 is 87, minus 7 is 80. So this formula does give us the correct values for n equals 1, n equals 2, and n equals 3. I will let you test 4 and 5 if you're interested in testing 4 and 5. And the last thing that remains to be done is finding the 10th term of the green sequence. Now that we have a formula, it's very easy to find the 10th term. We plug in n equals 10, and we get 3,000 minus 100 plus 50 minus 7. And if you work that all out, you get the 10th term of 2,943. Right, I hope you enjoyed, and I hope this wrapped up everything we've been talking about with sequences fairly well. I encourage you to ask people at home to make sequences for you and see if you can find them, maybe even an n to the 4th sequence. See if you can uncover them by this method of taking consecutive differences. Thank you.